about Gini impurity index. So my eventual goal is to talk about decision trees and random forests. And there are almost every learning models doesn't make sense. Almost every machine learning models, they have a loss function at the end, right? Objective function at the end, the thing that you want to optimize, maximize or minimize. And when it comes to building decision trees, there are two functions of choice. One is the entropy function that I discussed last week, and today we're doing another function called the Gini index. So let me first write down the formula. So let's say you have probability P1, P2, Pn equals to 1. So in other words, you have n classes. So you have n different classes, and you can just count the number of items in each class divided by the total number of items. So Pi would be like the size of the, if I say xi is the ith class, is the size of the xi divided by capital N, where capital N is the entire data set. Okay? So, and of course, if you do this, then if you add them up, it will be equal to 1. That's true for any probability. Now, in such a class, in such a case, you can talk about the Gini impurity index, and this is defined as 1 minus sum of Pi squared. Let's call this G of G as this. And the meaning of this is it's the probability of a randomly classified sample to be incorrect. Okay, so let's see why this makes sense. So first of all, let's just think about the three cases, three groups, okay, three classes. So let's just say you have P1 plus P2 plus P3. So in this case, let's talk about taking a random sample, and let's just say, oh, this is sample 1. You just randomly place it. Okay, so you just roll a dice and say, oh, it's just sample 1. Okay. Now, when you randomly classify, you probably want to classify using a dice that reflects the number of items in each, right? So if you had like 5 items in class 1 and 2 items in class 2 and 3 items in class 3, what you want to do is you want to make a spinner that has this amount of proportion so that this appears more than the other ones, right? So in this case, this probability will be 1/2, this probability will be 1/5, and this will be 3/10, right? So 5 over 10 is 1/2, 2 over 10 is 1/5. So they add to 1. So you're going to make a spinner so that half of it is 1, and then 2/3 will be 2, and then 2/10 will be 2, and 3/10 will be 3. So you roll this spinner and so you take a random sample, right? So you take a random item from here, and you forget which class it was from, okay? So imagine that you have something like red, blue, yellow, and then you have 3 groups, and you randomly pick something, and you just say, okay, this belongs to class number 1. You just randomly do it by just rolling a dice or doing a spinner, okay? Roll this spinner, and then if the spinner comes out as number 2, then you say, oh, this must be 2. Of course, in many cases it will be wrong, right? But let's try to figure out the probability of getting it right just by chance. How can you calculate? Well, let's say that so x is the random variable that says that tells you which class it is. So x could be 1 or 2 or 3. Now, what you want to know is the probability of x being classified as 1, okay, times the probability that x was from 1. Right. Plus probability that So let's think about what this means. You randomly select one item from the 10. What's the probability that it's going to be 1 from the group 1? 1/2, right? But then if you put it back randomly as classified randomly using this, what's the probability that you're going to correctly identify this group 1? It'll be 1/2, right? So it'll be 1/2 times 1/2. That's what this means, right? And this is, you randomly select an item. What's the probability that it will be from 2? It will be 2/10 or 1/5. Right? And again, if you randomly classify it, what's the probability that you would correctly classify it as from 2? It will be this, okay? So you do that. And this will be the probability of correctly classifying. So it's a probability that your random choice and classification is done correctly. Right? But then, if this is what it is, let me rewrite this again. So what is this? This is really P1, right? This is P1 times P1, so P1 squared. This is P2 times P2, so it's P2 squared plus P3 squared. Okay. So you see that sum of squares of the probability has the meaning that if you randomly select a sample from your population and classify it randomly using the proportion of the population, this is the probability you're going to get it correctly. Okay. And then, as you know, always if you want the probability of something that's not, then you subtract from 1, right? So this Gini impurity index is obtained by subtracting 1 minus correctly classified, so that you get the probability of incorrect classification. Right? That's why that's true. Is that okay? Yeah, that's Gini impurity index. And let's think about some extremes. What if you just have one class, 100%, just one group? What will be the Gini impurity index? Everything's the same.
0.
It'll be 0 because you just have one probability, which is P, right? And P would be 1 because everything has to add up to 1, and you just have one probability. And therefore, if you do 1 minus 1 squared, is 0. Okay. So that kind of gives you an idea of why this is called Gini impurity index, because it's 0, meaning it's very pure. Everything is the exact same thing, so there is no other foreign elements in this single group. Okay, and that will be that's a very important idea when making trees. Right? Now I want to give you a second formula because often in the literature some people write it like this. Some people write it like summation of pi 1 minus pi, just like that. That's another way to write it. And it's not so clear at first why those two formulas are the same. So let me just explain it with using, again, this example. So if you have 1 minus p1 squared plus p2 squared plus p3 squared, this will be the Gini impurity index for these three probabilities. What you want to do is you want to do 1 minus p1 minus p2 minus p3 plus p1 plus p2 plus p3 minus p1 squared plus p2 squared plus p3 squared. So notice that these two are the same because all I did was I subtracted p1, p2, p3 and added p1, p2, p3 back in. Right? It's exactly the same. Right? Agreed? What would this be? One. No.
Oh, no.
This is 1, right? Just subtracting this will be 0, right? So now what you have is p1 minus p1 squared plus p2 minus p2 squared plus p3 minus p3 squared. And that's same thing as p1 times 1 minus p1 plus p2 times 1 minus p2 plus p3 times 1 minus p3. Okay? Now, I like this formula better than this one because this tells us something that it's hard to read from here. When is this value small? When is the impurity small? When pi is close to 0 or pi is close to? When is this close to 0? 1, right? So you can see that if you have probabilities that are very small, then the Gini impurity index will be small, right? In other words, if your classes have one majority and a few others that are not the majority, if that's true, then you have lower impurity index. Okay?